So we're going to start off by doing our breadth first search implementation. And really, the breadth first search implementation is going to look really similar to a level order traversal of a binary search tree, just with adjustments to the underlying data structures that we're really working with when we do this kind of search. First off, we have to address the idea of an adjacency list and how we actually implement it. There are a lot of different ways that we can implement adjacency lists. The way that I'm going to show you first in this particular video is using a dictionary. A dictionary could be a really good way of storing an adjacency list because we can have the keys in the dictionary be the nodes in our graph, and then we can have the nodes that are adjacent to that node be the values that are associated with it. We just have an array associated with a key inside of a dictionary. So that's one option that we have for our adjacency lists. In future videos, we'll see that we can also store adjacency lists inside of an array, where each entry in the array is another array, and that could be a way that we can represent this as well, although I think that it's generally closer to an adjacency matrix more than it is an adjacency list, so I'm going to use the dictionary approach for the time being. So basically the way that I'm going to set this up is I'm going to create a class called graph. And the class graph that we're going to be working with is just going to have its adjacency list as its main property. And we're going to have one property, or one method inside of it rather, which is called add edge. And it's going to add an edge between u and v. Now, what's important with this sort of process is that we want to consider if our graph is directed or undirected. If our graph is directed, when we add an adjacency for u, we also have to add an adjacency for v because the edges move in both directions, right? If our graph were to be directed, we would only have to add one edge for the one direction. So for this case here, I'm going to call this an undirected graph, and we're going to assume that we're working with that just because it's probably the more code to implement. So I want to show you sort of the longer version. Then I'll just show you briefly the directed version as well. So if we're adding an edge in an undirected graph, what we're going to do is we're going to say if u is in the adjacency list, I just realized that I didn't initialize this. This will be a dictionary, right? So if u is in the adjacency list already, then we're going to take that adjacency list at u and we're going to append v. So remember, we're creating a list of the adjacencies. We append it to that adjacency list. Otherwise, if it's not, then I'm going to set the adjacency at u to be equal to an array whose only entry is v. And then similarly, I'm going to say if v is in self.adjacency, then I'm going to add it to v's list. Otherwise, I'm just going to create a new entry at v, which is a single array with the value of u. So that's the way that we're going to add an edge. Now, I want to show you the directed version of this as well, because it's a slight difference, right? So if I wanted to say directed, right, basically all that's going to change is I'm just going to assume that it's an edge from u to v. So we only need this first part here. Basically, you see that we just don't create the edge in both directions between u and v and u. We just create it from u to v because it is directed. So that's the only difference between those two. I just wanted to show that for you to have as a reference as well. We're primarily going to be working with the undirected version since breadth first search works with pretty well any graph that we have, and undirected is probably the easier case of them. So we'll take a look at that undirected breadth first search here. So the idea here is basically that we could set up a graph now, right? So G is equal to a graph, and I could just generally say add some edges to that graph, right? And I'll just add a bunch of different edges for us to be able to have inside of our graph, and then we'll do a breadth first search on these different edges, okay? So let me just add a few different edges. So I have an edge between 1, 3, 1, 4, and then we'll just do a 2, 4. Just as an example graph, and you can really set up any graph that you would like. Just visualize in your head how the edges are going to be connected when you set it up, and make sure that it has like paths around it that you can test out for a breadth first search, and you'll be all good. The setup for a breadth first search, we'll set it up as a method instead of our graph, because I think that that's probably the easiest way to sort of see this in action. We could also have it as a separate method that takes in a graph. It's really up to you. It doesn't make too much of a difference, right? And the very first way that I'm going to show this is just through an iteration doing a breadth first search. So I'm going to show you how we actually end up searching the graph when we do a breadth first search. Then we'll modify this to actually search for a target. So in this example here, we don't need the adjacency here. We just need S, which is our source. This is the starting point where we're going to start our breadth first search. And what we're going to use for this is a queue. Same queue that we used for our tree, which is our node queue. So I'll say from node queue import queue. And then generally all we're going to do is we're going to keep track of the different nodes that we visited, which I'm going to place inside of a dictionary. And what I do is I start by saying that we have visited the source node, and then I onqueue that node. And then what I do is I say while queue.size is greater than 0, so while there's still something on the queue, I'm going to dequeue what's currently on the queue. I'm then going to print that value. And then I'm going to say for x in the adjacency at current. So I'm going to iterate through all of the different adjacencies that exist for this node. I'm going to say if those adjacencies have not been visited, then I'm going to add them into my dictionary as visited first. Then I'm going to onqueue them to my queue. This process will continue until we have iterated through all of the possible adjacencies from our source. So let's go ahead and give that a try and see what ends up happening. Again, this is just going to print out the nodes as if we were searching through it as a breadth first search. I just want you to see first how that ends up looking, and then we'll actually do a search on our graph itself. And we'll see here, oh, it's just missing a positional argument for source. So we'll start it at node 0. Do you see it starts at 0 and it goes to its adjacency 1. Then it goes to the next adjacency of 0, which is 2, right? Then it goes to 1's adjacency, which is 3, and then 1's adjacency, which is 4. And notice that 2, 4 doesn't happen because we already visited 4, so we don't have to visit 4 twice, so it only iterates through and visits every node once. So you can see generally how that's iterating through, right? It just starts at its source, it goes to all of the adjacent things to that source, it then goes to the adjacent things of the next node that it saw, and it continues on like this, right? So very similar to the level order traversal that we saw. Now the question is, how can we modify this for searching? And that process is actually pretty straightforward. Basically, all we do is we take an additional argument, which is a target node that we're trying to reach. And basically, we're going to keep track of whether or not we have found the node. So we'll say found equals false. And we're going to iterate through while the queue size is greater than 0 and we have not found what we're looking for. What we're going to do is we're going to say when we check the adjacencies, we're going to generally check to see if the value x is equal to the target. And if it is, found is going to be equal to true. Actually, probably the better way of setting this up is to do it here where we print the current value, right? So we could just check to see if current is equal to target, and if it is, found is going to be equal to true. And then we can exit out once we've found that value, right? And then what we could do at the end here is we could just go ahead and return found as a result, right? So that generally would be the process that we would have here, right? There we go. So let's take a look at how that ends up working. So suppose I wanted to see if I can get from 0 to 4, right? And when I'm looking at this, I feel that I can, right? If I start at 0 and I go to 2, and I go from 2 to 4, I could reach 4, or I could go from 0 to 1 and from 1 to 4, and that would take me to 4 as well. So let's take a look and see what ends up happening with this search. So if I do my breadth first search, you'll see that it goes through 0, 1, 2, 3, 4, and we end up with a true because it did find the node that it was looking for. Now, if I gave it a node that, wasn't the one that it was looking for, you'll see that it gives me false after searching through the whole thing. Now, if I give it a node that's sort of closer perhaps to the beginning, you'll see that once it gets to 2, it exits and it's done searching. If I gave it the source node, we would see that it would also exit on that source node. So it looks like this works pretty reliably as a search through our graph. So generally the final question here is, well, what is the time complexity of this algorithm? And it turns out that it's a little bit different from the time complexities we've seen so far. When we describe time complexities with graphs, we often describe them as a function of the number of vertices and the number of edges in our graph. With breadth first search, we say that it's an OV plus E algorithm, where V is the number of vertices and E is the number of edges. So basically, it's the total number of vertices plus edges gives us the time complexity of our graph. The reason for that is because it, of course, has to iterate all of the vertices in the graph in the worst case. Well, generally, if the graph is going to be connected, right, it would iterate through all of the different vertices. And in turn, it has to check all the different edges because it checks all the adjacencies at each node that it reaches. So you see that it ends up iterating through all the vertices and edges inside of our graph. So this is, again, just one approach that we can use to search through a graph. So you've now seen a breadth-first search. In the next video, we're going to take a look at a depth-first search. So thanks so much for watching, and I'll see you in the next video.